63 light years from where you're sitting right now, there is a star. It's young, barely a toddler by stellar standards, surrounded by a glittering tilted disk of dust and rock that looks from Earth almost exactly edge-on. Astronomers have been staring at this star for over 40 years. It has its own Wikipedia-famous nickname. It's been photographed by nearly every major telescope humanity has ever built. Entire careers have been built studying it. And for 40 years, it was hiding something from us. Not a small something, not a moon, not an asteroid, not a comet. A planet. A giant planet, at least twice the mass of Jupiter, sitting right there in the data the entire time. Camouflaged so well that it took the most powerful space telescope ever constructed, using a detection method nobody had successfully used this way before, to finally catch it in the act. This is the story of Beta Pictoris d. It's a story about a star system so well studied that astronomers thought they knew all its secrets. It's a story about dust, ordinary, unglamorous cosmic dust, being clever enough to hide a world twice the size of Jupiter in plain sight. And it's a story about a completely new way of finding planets, one that doesn't rely on seeing them at all, but on reading the chemical fingerprint of their breath scattered across space. By the end of this video, you're going to understand exactly how astronomers pulled off one of the most technically impressive exoplanet discoveries of the decade, and why the method they used might be about to change exoplanet science forever. Let's start at the beginning. Let's talk about the star that started it all. To understand why the discovery of Beta Pictoris d is such a big deal, you first need to understand just how much history is packed into this one star system. Beta Pictoris isn't some obscure entry in a catalog. It is, without exaggeration, one of the most important stars in the entire history of exoplanet science. Beta Pictoris sits in the southern constellation, Pictor, the painter's easel, a faint and fairly unremarkable constellation invented in the 18th century, mostly to fill an empty patch of southern sky. The star itself, though, is anything but unremarkable. It's roughly 1.75 times the mass of our Sun, burning hot and blue-white, and it's young. Astronomers estimate its age at around 20 to 26 million years old. To put that in perspective, our own Sun is about 4.6 billion years old. If you scaled the Sun's life down to a single human lifetime of 80 years, Beta Pictoris would be roughly 4 months old. It is a newborn, cosmically speaking, and newborn stars are exactly where the action is if you want to understand how planets form. Here's why astronomers fell in love with this star in the first place. Back in 1983, the Infrared Astronomical Satellite, IRAS, one of the first space telescopes designed to see an infrared light, noticed that Beta Pictoris was radiating far more infrared light than a star of its type should. That excess infrared glow is a telltale sign of warm dust. Something around that star was absorbing starlight and re-radiating it as heat. The following year, in 1984, astronomers Bradford Smith and Richard Terrell pointed a coronagraph, a device that blocks out the blinding light of a star so you can see faint things around, at Beta Pictoris from the Las Campanas Observatory in Chile. What they found made headlines around the world. They imaged an enormous, flattened disk of dust and debris extending outward from the star, seen almost perfectly edge-on from our vantage point on Earth. It was the first time humans had ever directly photographed a disk of material around another star visual, undeniable evidence that planetary systems form from disks of dust and gas, exactly as theorists had predicted. That image, grainy and strange, as it looks by today's standards, is one of the foundational pictures in the history of astronomy. It transformed Beta Pictoris from just another star into a proving ground, a place where scientists could watch the process of planet formation unfold, frozen at one particular moment in time, 63 light years away. Over the following decades, Beta Pictoris kept surprising people. Astronomers noticed warps and asymmetries in the disk, subtle distortions in its shape that couldn't be explained by dust alone. Something massive had to be gravitationally sculpting that disk, something unseen. For over 20 years, that something remained a mystery. Theorists modeled it. Observers hunted for it. And then, in 2008, and confirmed in 2009, a team using the Very Large Telescope in Chile finally captured direct images of a planet, Beta Pictoris b. It was a landmark. Beta Pictoris b became one of the very first exoplanets ever directly imaged, meaning astronomers didn't infer its existence indirectly, through a wobbling star or a dimming light curve, but actually captured photons of light coming from the planet itself. It's a gas giant several times the mass of Jupiter, orbiting relatively close to its star, and its discovery confirmed what everyone had suspected. This disk had planets embedded in it, and those planets were massive enough to warp the dust around them. If the story stopped there, Beta Pictoris would already be one of the most important stars in exoplanet history. But it didn't stop there. In 2019, astronomers announced a second directly imaged planet in the system, Beta Pictoris c, found through a combination of direct imaging and a technique called radial velocity, which detects the tiny gravitational tug a planet exerts on its host star. Beta Pictoris c orbits closer to the star than b, and its discovery made Beta Pictoris one of the very few systems in the galaxy known to host more than one directly imaged planet. Think about what that means. Out of the more than 5,000 confirmed exoplanets astronomers have found, the overwhelming majority discovered through indirect methods like transits or radial velocity. Only a small, elite handful have ever been directly imaged. Direct imaging is punishingly difficult. It requires blocking out a star that is millions to billions of times brighter than the planet you're trying to see, while that planet sits at an angular separation from its star. From our perspective on Earth, that's often smaller than the width of a coin held miles away. Beta Pictoris, with 2 directly imaged planets, was already an astonishingly rare company. So by the early 2020s, the scientific picture of Beta Pictoris looked settled, at least in broad strokes. You had a young star. You had a spectacular, well-mapped debris disk. You had 2 confirmed giant planets, B and C, both found through painstaking direct imaging campaigns using some of the best ground-based telescopes on Earth. Instruments with names like Sphere and GPI, purpose-built to hunt for faint planetary light next to overwhelming starlight. Astronomers had every reason to believe they'd found what there was to find. This system had been imaged, re-imaged, modeled, and remodeled for 4 decades. If there was a third giant planet hiding in there, surely someone would have seen it by now. They hadn't. And the reason they hadn't is the whole reason this story is interesting. Before we get to the discovery itself, we need to talk about why finding planets around other stars is so absurdly difficult in the first place, and specifically, why Beta Pictoris presented a uniquely nasty version of that problem. Here's an analogy astronomers like to use. Imagine you're standing in Los Angeles, and somebody in New York City is holding up a firefly next to a lighthouse, and they ask you to spot the firefly using a telescope. That's roughly the challenge of directly imaging an exoplanet. Stars are so much brighter than the planets orbiting them, often by a factor of 1 billion or more in visible light, that the glare completely swamps any light reflecting or radiating off the planet. Astronomers get around part of this problem with coronagraphs, physical or digital masks that block out the central starlight, letting the much fainter light around it become visible. They also benefit from observing planets in infrared light rather than visible light, because young, warm giant planets glow with their own residual heat from formation, and that thermal glow is relatively brighter in infrared wavelengths, improving the contrast between planet and star. That's exactly how Beta Pictoris b and c were found. Coronagraphic direct imaging in the infrared, painstakingly separating a faint point of planetary light from the overwhelming glow of the star. Now add a second problem on top of the first: dust. Beta Pictoris doesn't just have a bright star. It has one of the brightest, most massive debris disks known in the galaxy. A huge structure of dust and rocky debris, the leftover construction material from planet formation, extending for tens of billions of miles outward from the star. That dust does something very inconvenient if you're trying to find a planet. It scatters starlight in every direction, creating a kind of glowing haze or fog that fills the region around the star. If a planet happens to be sitting inside or near that dusty structure, from our point of view, its faint light gets buried inside the scattered glow of the disk itself. It's not just one bright point of light you need to block out anymore. It's a bright point of light plus a diffuse, complicated, scattered halo of reflected starlight, and somewhere inside that halo might be a planet's worth of photons, utterly indistinguishable, at least to a coronagraph, from the dust glow surrounding it. Researchers described Beta Pictoris D's situation almost exactly this way: a planet concealed within one of the brightest known debris disks in the galaxy, with the dust functioning much like fog, making it extraordinarily difficult for conventional imaging to tell a planet apart from the structure around it. This is the trap that hid Beta Pictoris D for so long. It wasn't that nobody looked. Astronomers pointed some of the best direct imaging instruments on the planet, literally purpose-built to separate faint, planetary light from bright stellar glare, straight at this system repeatedly for years. But every time, the planet's signal was buried inside the fog. Here's an important nuance, though, because it explains why the eventual discovery method was so clever. Beta Pictoris D wasn't undetectable because it was too faint in an absolute sense. It was undetectable because the specific detection method being used, looking for a bright point of light against a background, happened to be the wrong tool for this particular disguise. It's the same reason you can't find a specific grain of white sand on a white sand beach by looking for something white. You need a different kind of signal. You need something that distinguishes the object not by brightness, but by some other property entirely. And that's exactly the pivot that made this discovery possible. Instead of asking, "Can we see a bright dot where there wasn't one before?" the team asked a completely different question. Can we detect the unique chemistry of a planet's atmosphere, even if we can't cleanly separate its light from the fog around it? That question, and the telescope built to answer it, is where the story of James Webb comes in. The James Webb Space Telescope, launched on Christmas Day 2021, and now stationed nearly 1,000,000 miles from Earth at the second Lagrange point, is often talked about for its ability to see the earliest galaxies in the universe or capture jaw-dropping images of nebulae. But one of its quieter superpowers, arguably just as revolutionary, is its ability to perform extremely sensitive spectroscopy, splitting light apart into its component wavelengths to read the chemical fingerprint hidden inside it. Every chemical element and molecule absorbs and emits light at very specific wavelengths, a kind of barcode unique to that substance. When starlight passes through or reflects off a planetary atmosphere, some of that light gets absorbed at exactly the wavelengths associated with whatever molecules are present in that atmosphere. Water vapor leaves one signature. Carbon monoxide leaves another. Methane leaves a third. If you can capture enough of that light and spread it out into a detailed spectrum, you can read those absorption patterns and know, with remarkable confidence, what's actually out there, even in situations where you can't cleanly form a crisp, clean image of the object producing that light. This is what makes Webb different from previous generations of instruments used to hunt for planets like these. Webb carries an instrument called NIRSpec, the near-infrared spectrograph, and specifically its integral field unit, or IFU. An integral field unit is a special kind of instrument that doesn't just take a single spectrum of a single point in the sky. Instead, it captures a spectrum for every single pixel across a small patch of sky simultaneously. Instead of one measurement, you get thousands of tiny individual spectra, one for every location within the observed field, essentially building a 3D data cube. 2 spatial dimensions, plus a third dimension of wavelength at every single point. Why does that matter here? Because it lets you separate signals spatially and chemically at the same time. If there's a planet buried inside the scattered glow of a disk, and that planet's atmosphere has a distinct chemical signature different from the surrounding dust, an integral field spectrograph gives you the tool to go pixel by pixel, comparing the spectral fingerprint at each location, hunting for the one spot where the chemistry doesn't match the dusty background, the one spot that looks like an atmosphere instead of scattered starlight. That's the technique researchers used on Beta Pictoris. They pointed Webb's NIRSpec IFU at the system, originally intending to study another target within it, and mapped out the chemical composition across the region around the star, essentially building a detailed chemical map of the whole environment. And buried inside that chemical map was something that didn't belong. A signal rich in carbon monoxide, with additional hints suggesting water vapor, distinct from the surrounding dust and gas. The signal had the telltale chemical stamp of a planetary atmosphere, not scattered dust reflecting starlight, an actual atmosphere glowing with its own set of molecular fingerprints, sitting at a specific location within the system. This was the moment the team began to suspect they weren't looking at background structure anymore. They were looking at a planet. One member of the science team later described the power of this method in a simple way. Obtaining a spectrum at the same time as an image lets you quickly confirm your suspicions, because a spectrum alone contains an enormous amount of information, far more than a single point of brightness ever could. That's really the heart of what made this discovery possible. A conventional coronagraphic image gives you one crucial piece of information. Is there a bright dot here or not? A spectrum gives you dozens of pieces of information simultaneously. What molecules are present, roughly how worn the object is, and crucially, as we'll get to in a moment, how fast it's moving and in which direction. This was a genuinely new way of hunting for a hidden world. And the fact that it worked on one of the toughest, dustiest, most well-studied systems in the sky is exactly why astronomers are so excited about what it might mean for every other messy, dusty planetary system out there. Finding a strange, unexplained signal in your data is one thing. Proving that signal is actually a planet and not some kind of artifact, some quirk of the dust, some contamination in the instrument, is an entirely different and much harder task. This is where the story gets into some of the most satisfying science of the whole discovery, the confirmation process. The first and most powerful piece of confirming evidence came from something spectroscopy is uniquely good at measuring: radial velocity. Radial velocity describes how fast an object is moving directly toward or away from an observer, and it's measurable through something called the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches you and lower-pitched as it moves away. Light does something analogous. Light from an object moving toward you gets slightly compressed toward bluer wavelengths, and light from an object moving away gets slightly stretched toward redder wavelengths. By measuring exactly how much the absorption lines in the newly discovered planet's spectrum were shifted, the team could calculate precisely how fast this object was moving toward or away from Earth at the moment of observation. Now, here's why that mattered so much. A background contaminant, some clump of scattered dust, some instrumental glitch, has no reason to be moving at a velocity consistent with an object in a stable, gravitationally bound orbit around Beta Pictoris. But a real planet does. A real planet orbiting a star at a particular distance should be moving at a very particular physics-dictated speed, in a very particular direction, depending on where in its orbit it happens to be at that moment and how that orbit is tilted relative to our line of sight. When the team calculated the predicted radial velocity for a planet in a stable orbit consistent with the disk's geometry and compared it to the actual measured velocity of their mystery signal, the numbers lined up. The object's speed, its position, and its alignment with the debris disk all matched what you'd expect from a genuine planet in orbit around Beta Pictoris. That's an extraordinarily hard thing to fake by accident. Dust doesn't know what velocity a planet is supposed to have. Only an actual gravitationally bound orbiting body would show up with exactly the motion physics predicts. That was compelling evidence on its own. But good science demands more than one line of evidence, especially for a claim this significant, in a system this famous, where any mistake would be picked apart by the entire exoplanet community. So the researchers pursued follow-up observations to nail things down even further. They obtained director's discretionary time, a special allocation of extremely valuable Webb observing time, granted outside the normal competitive proposal process for particularly time-sensitive or high-priority science, to point Webb's MIRI instrument, the mid-infrared instrument, at the same location. MIRI operates at longer infrared wavelengths than NIRSpec, sensitive to a different slice of the chemical spectrum. And when they looked, MIRI detected additional molecular fingerprints, methane, alongside further confirmation of water vapor. This wasn't just the same signal seen twice. It was independent confirmation from a completely different instrument sensitive to different wavelengths, turning up more pieces of the same underlying picture. A cool, giant, gas-rich atmosphere sitting exactly where the NIRSpec data had first flagged something unusual. And then, in a genuinely remarkable piece of scientific timing, a second entirely independent team weighed in. Working separately, researchers led by Ben Sutcliffe of the University of Edinburgh and Marcus Bonds of the European Southern Observatory used data from the European Southern Observatory's Very Large Telescope, combined with Webb's own near-infrared camera, to independently confirm the planet's existence through direct imaging analysis. In other words, two separate research efforts, using different instruments, different telescopes, and at least partially different techniques, converged on the same conclusion at roughly the same time. There really was a third giant planet hiding in the Beta Pictoris system. That kind of independent cross-validation is about as strong as confirmation gets in observational astronomy. When two separate groups, working with different data and different methods, land on the same answer without coordinating in advance, it dramatically raises confidence that what you're looking at is real and not an artifact of any one particular instrument or analysis pipeline. With the radial velocity matching orbital predictions, with multiple molecular signatures confirmed across two different Webb instruments, and with an entirely independent imaging confirmation from ground-based telescopes, the case was closed. Beta Pictoris had a third giant planet. It was given the designation Beta Pictoris d, continuing the standard naming convention where the host star keeps its letter, and planets are labeled B, C, D, and so on in the order they were discovered, not necessarily the order of their distance from the star. Beta Pictoris officially became only the second known planetary system, out of the thousands catalogued so far, confirmed to host at least 3 directly detected giant planets. That's an extraordinary rarity, and it puts this system in an incredibly small, elite club of multi-planet systems where astronomers have actually detected more than one planet through direct means, rather than indirect statistical inference. So now that we know how astronomers found it and how they confirmed it, let's talk about what Beta Pictoris d actually is, what we currently know, and how confident we can be in each of those numbers. Mass first. Current estimates place Beta Pictoris d at somewhere between roughly 2 and 4 times the mass of Jupiter, with some analyses favoring an estimate around 2 times Jupiter's mass as a likely lower bound. To put that into perspective, Jupiter itself is already about 318 times the mass of Earth. A planet with 2 to 4 times Jupiter's mass is an absolutely enormous world, firmly in gas giant territory, likely composed primarily of hydrogen and helium with a mixture of heavier elements, much like Jupiter and Saturn in our own solar system, just considerably more massive. Interestingly, current estimates suggest Beta Pictoris d may actually be the least massive of the 3 known planets in the system, smaller than both B and C in terms of mass, even though it has the widest orbit of the 3. That's a detail worth sitting with for a second, because it tells you something about how this system's planets are arranged. The innermost planets appear to be somewhat more massive than the outer one currently known, though these estimates carry real uncertainty and are likely to be refined as more data comes in. Orbit next. Beta Pictoris d appears to orbit its star at a distance of roughly 30 astronomical units, meaning about 30 times the distance between the Earth and the Sun. If you're looking for an intuitive comparison, that's remarkably similar to the distance Neptune sits from our own Sun, which orbits at about 30 astronomical units as well. So imagine picking up our solar system's Neptune, replacing it with something 2 to 4 times heavier than Jupiter, and dropping it into orbit around a young, hot, blue-white star instead of our Sun. That's roughly the picture. This orbital distance places Beta Pictoris d beyond the orbit of Beta Pictoris b, making it the outermost of the 3 known planets, while still situating it inside the inner edge of the system's enormous debris disk. That last detail is architecturally important. It means the planet is nestled just inside the disk's boundary, in exactly the kind of position where its gravity could plausibly be sculpting the disk's inner structure, potentially helping explain some of those decades-old mysteries about warps, gaps, and asymmetries that astronomers had puzzled over since the earliest images of the disk back in the 1980s. Temperature and atmosphere. The molecular signatures detected, carbon monoxide, water vapor, and methane, paint a picture of a relatively cool giant planet atmosphere by the standards of newly formed gas giants, consistent with a young, still cooling world that formed relatively recently in astronomical terms and hasn't yet radiated away all of the heat left over from its formation. The presence of methane specifically is notable because methane tends to be more prominent in cooler planetary atmospheres. On warmer young giant planets, carbon tends to exist more as carbon monoxide, while cooler atmospheres favor methane instead. Detecting both suggests a planet sitting in an interesting middle ground temperature regime and gives modelers real data to test their atmospheric chemistry models against, rather than just theoretical predictions. It's worth pausing to appreciate just how much information came bundled together in this single discovery. Traditional direct imaging tells you, here's a dot of light, and from its brightness in a couple of different filters, we can make a rough guess about temperature and mass using theoretical cooling models. Spectroscopy, by contrast, handed astronomers a genuine molecular inventory, an orbital velocity measurement, and a mass estimate essentially all at once, from the same set of observations that revealed the planet's existence in the first place. That's the enormous efficiency gain researchers were pointing to when they emphasized what this new detection method offers. Instead of a multi-year process of first finding a dot, then years of separate follow-up spectroscopy to characterize it, you get discovery and characterization essentially simultaneously. Now, some healthy scientific humility here. These are still early-stage estimates. Mass estimates derived from atmospheric models and orbital dynamics always carry uncertainty. And as researchers gather more observations, more time on Webb, more radial velocity measurements at different points in the planet's orbit, more detailed atmospheric modeling, these numbers will almost certainly get refined and might shift somewhat from the initial estimates released alongside the discovery announcement. That's normal, healthy science. Initial discovery papers give you the best answer available with the data on hand. The numbers sharpen over subsequent years, sometimes dramatically. What won't change, though, is the core fact. There is a giant planet, roughly Neptune's orbital distance from its star, sitting inside one of the most famous and well-studied debris disks in the galaxy, and it took a fundamentally new detection technique to finally reveal it. Let's zoom out from Beta Pictoris d itself for a moment and talk about why this discovery matters beyond just we found one more planet. Because the story of the debris disk successfully hiding a planet for 4 decades tells us something important about how planetary systems evolve, and Beta Pictoris d's discovery might help crack open a mystery that's been sitting there since the very first disk image in 1984. Remember those warps, gaps, and asymmetries astronomers noticed in the Beta Pictoris disk over the decades? For a long time, researchers suspected these features were caused by the gravitational influence of unseen planets, tugging and sculpting the disk material as they orbited. Beta Pictoris b's discovery helped explain some of these features, but not all of them. Some structural quirks in the disk never quite matched up cleanly with the gravitational influence of just 2 known planets. A newly confirmed planet orbiting right at the inner edge of the disk, exactly where Beta Pictoris d sits, is a very promising candidate for explaining at least some of these remaining puzzles. A planet in that position would be expected to clear out material directly in its orbital path, create resonant structures where dust particles get gravitationally parked in stable configurations, and potentially help explain clumps or gaps that show up when astronomers image the disk in detail. This is one of the most elegant parts of the whole story. The dust that hid Beta Pictoris d for 40 years is very likely the same dust that Beta Pictoris d has been shaping, gravitationally, the entire time. The planet wasn't just hiding in the fog. In a very real sense, it may have been helping create the fog structure, all while investigators searched right past it. There's a broader lesson buried in here about planet formation generally. Debris disks like the one around Beta Pictoris are essentially the leftover construction debris from building a planetary system. The rocky and icy material that didn't get incorporated into planets, ground down over millions of years of collisions into smaller and smaller fragments, eventually becoming the fine dust that scatters starlight and creates that fog effect. Studying how that dust is distributed and how it's been shaped by embedded planets gives astronomers a kind of forensic record of the planet formation process, evidence of which planets are where and how massive they are, based purely on the gravitational fingerprints they leave in the surrounding debris. Before Beta Pictoris d's discovery, astronomers had to infer planetary presence purely from these disk sculpting clues, an indirect and often ambiguous approach, since multiple different planetary configurations can sometimes produce similar-looking disk features. Now, with an actual confirmed planet located at the inner edge of the disk, researchers finally have ground truth to test their disk sculpting models against. Every theoretical prediction about how a giant planet at 30 astronomical units should shape the surrounding debris can now be checked against an actual, confirmed, characterized planet sitting right there. This is exactly the kind of feedback loop that moves a whole field of science forward. You had decades of disk observations generating hypotheses about hidden planets. Now you have a confirmed planet that can be used to test and refine those very hypotheses, which in turn will sharpen future searches for hidden planets in other dusty systems across the galaxy. And that leads directly into arguably the single biggest implication of this whole discovery, bigger, in some ways, than the planet itself. Here's the sentence that made this discovery ripple through the exoplanet science community far beyond just cool. One more planet found. Beta Pictoris d is the first directly imaged planet discovered primarily through moderate resolution spectroscopy rather than traditional coronagraphic direct imaging. That's not just a technical footnote. That's potentially a new toolkit for an entire field. Think back to the fundamental problem we discussed earlier. Dusty, complicated environments defeat traditional direct imaging because they turn a clean, is there a bright dot here or not? Question into a messy, there's scattered light everywhere, good luck situation. Debris disks aren't rare. Many young planetary systems have them, in various stages of density and complexity. If dusty environments have been quietly hiding planets in other systems, the same way Beta Pictoris hid this one, then a huge number of worlds might be sitting undiscovered, simply because nobody had the right tool to look for their chemical signature rather than their raw brightness. The technique demonstrated here essentially flips the search strategy. Instead of asking, where is there a point of light distinguishable from the background, you ask, where is there a chemical signature distinguishable from the background? Dust reflects starlight in a relatively smooth, featureless way across a spectrum. It doesn't have sharp absorption features from specific molecules the way a planetary atmosphere does. That gives astronomers a genuinely different axis to search along, one that doesn't care nearly as much whether the planet's light is spatially blended into a bright, fuzzy disk, because you're not primarily relying on spatial separation anymore. You're relying on spectral separation. This has an enormous, very practical advantage: efficiency. As one researcher on the Discovery team put it, obtaining a spectrum at the same time as an image lets you immediately begin investigating a candidate object's properties in the very same observation that revealed it in the first place. Traditionally, exoplanet science has followed a two-stage process. First, spend years of telescope time hunting for a faint point of light through direct imaging surveys. Then, once you've found a candidate, spend additional years securing follow-up spectroscopic observations to actually characterize what that point of light represents, its temperature, its composition, its likely mass. The Beta Pictoris D method compresses that entire pipeline. Discovery and characterization happen essentially simultaneously from the same dataset. That efficiency matters enormously given how scarce and competitive time on an instrument like Webb actually is. Every hour of Webb observing time is intensely oversubscribed, requested by scientists across the globe for an enormous range of projects, from the earliest galaxies in the universe to nearby exoplanet atmospheres. A technique that lets you discover and characterize a planet in the same observing block, rather than needing separate imaging and follow-up spectroscopy campaigns spread out over years, is a genuinely valuable efficiency gain for the entire field. There's also a subtler implication worth dwelling on. This method doesn't just help find planets hidden in dusty disks. It changes what counts as a good target for exoplanet searches in the first place. Historically, astronomers doing direct imaging surveys have often deliberately avoided extremely dusty, disk-rich systems precisely because the scattered light makes conventional imaging so much harder, biasing our planetary census toward cleaner, less cluttered systems. If moderate resolution spectroscopy proves broadly effective at cutting through that clutter, some of the most promising hunting grounds for future discoveries might actually be the messiest, dustiest, most difficult systems in the sky, the very places astronomers might previously have deprioritized. Naturally, there are caveats and open questions the field still needs to work through. This technique required an enormous amount of sensitivity and spectral resolution, meaning it's likely to work best for particularly favorable combinations of planet brightness, atmospheric chemistry, and disk geometry. Not every hidden planet in every dusty disk will necessarily produce a signal this clean and this confirmable. Researchers will need to test this approach across a broader range of systems to understand its real limits. How faint a planet can be and still be detected this way. How complex a disk's chemistry can get before it starts masking planetary signatures instead of merely surrounding them. And how much observing time is realistically required to apply this method as a general search strategy rather than a happy accident that worked spectacularly well in one famous system. But even with those open questions, the demonstration itself is the headline. Proof of concept has been established. A hidden giant planet, buried in scattered starlight and dust for 4 decades, was found by reading its atmospheric chemistry rather than searching for its silhouette. That's a genuinely new tool in the astronomer's toolkit. And tools like that tend to get used again, and again, and again, on every dusty system where researchers previously assumed there was nothing left to find. Let's take a step back and place this discovery in the wider context of exoplanet science as a whole. Because Beta Pictoris d isn't happening in isolation, it's landing at a moment when the entire field of direct imaging is maturing rapidly. Direct imaging remains one of the rarest and most technically demanding ways to discover a planet. The overwhelming majority of the more than 5,000 exoplanets confirmed to date were found using indirect methods. The transit method, which detects the tiny dimming of a star's light as a planet crosses in front of it, used spectacularly by missions like Kepler and TESS. And the radial velocity method, which detects the gravitational wobble a planet induces in its host star. Both methods are extraordinarily productive, but both come with inherent biases. They tend to favor planets orbiting relatively close to their stars, where transits are more frequent and gravitational tugs are stronger and easier to measure. Direct imaging fills a completely different niche. It's best suited to detecting large, young, warm planets orbiting relatively far from their host stars, precisely the opposite region of parameter space the transit and radial velocity surveys are naturally biased toward. That makes direct imaging an essential complementary technique, even though it currently accounts for a comparatively small fraction of total confirmed exoplanets. Famous direct imaging systems include HR 8799, with 4 image giant planets, and the systems around stars like Fomalhaut and PDS 70, the latter notable for showing planets apparently still in the process of formation, embedded in their birth disk. Beta Pictoris, with now 3 confirmed giant planets found through direct or spectroscopic means, sits right alongside HR 8799 as one of only 2 known systems with 3 or more directly detected planets. That's an extraordinarily short list, and it puts Beta Pictoris in genuinely rarefied scientific territory. What makes this moment particularly exciting is the convergence of tools now available to astronomers. Ground-based instruments like the Very Large Telescope's Sphere instrument and the Gemini planet imager have spent over a decade refining coronagraphic direct imaging techniques. Space-based infrared spectroscopy through Webb has now demonstrated an entirely complementary detection channel. And upcoming instruments, including next-generation ground-based extremely large telescopes currently under construction, capable of even sharper angular resolution than anything available today, promise to push both techniques even further in the years ahead. Systems like Beta Pictoris function as testbeds where all of these techniques get thrown at the same target, cross-validated against each other, refined, and improved. Every lesson learned hunting for hidden planets in this one famous, messy, dusty system becomes a transferable skill applicable to the thousands of other young planetary systems astronomers are eager to study, many of which are considerably fainter, farther away, and harder to observe in this much detail. There's also a longer-term significance worth mentioning. Young systems like Beta Pictoris are essentially time capsules, letting astronomers study planet formation in progress, or at least not long after it concluded, rather than trying to reverse engineer formation history from old settled systems like our own solar system, where most of the direct evidence of formation has long since been erased by billions of years of subsequent evolution. Every additional confirmed planet in a young system like this adds another data point to models of how giant planets form, how far out from their stars they tend to form, how disks get sculpted by embedded planets, and how planetary architectures evolve and settle over the following hundreds of millions of years. Beta Pictoris d, in other words, isn't just a newly discovered world. It's a newly discovered data point that helps calibrate our entire understanding of how planetary systems, including, ultimately, our own, come into being. So where does the story go from here? What are astronomers planning to do with this discovery? And what should we expect over the coming months and years? The immediate priority is refinement. The current estimates for Beta Pictoris D's mass, exact orbital parameters, and atmospheric composition are based on the observations available so far, and researchers will continue examining Webb's existing data, along with pursuing additional observing time, to sharpen every one of those numbers. Getting a more precise orbital solution requires additional radial velocity measurements at different points along the planet's path around the star, ideally spread out over a meaningful fraction of its orbital period, though with an estimated orbital distance around 30 astronomical units. A full orbit likely takes well over a century, meaning astronomers won't be watching a complete lap anytime soon, but rather refining the orbit through incremental measurements and modeling. The same way, astronomers have long tracked planets whose orbital periods vastly exceed a human lifetime. Atmospheric modeling is another major front. With confirmed detections of carbon monoxide, water vapor, and methane in hand, atmospheric chemists and modelers now have real data points to plug into sophisticated computer models of giant planet atmospheres. Models that predict things like cloud formation, temperature structure at different depths in the atmosphere, and how the balance between different carbon-bearing molecules shifts with temperature and pressure. Refining these models using an actual confirmed planet's data, rather than purely theoretical predictions, helps improve our understanding of giant planet atmospheres across the board, including, eventually, feeding back into how we interpret atmospheres on other, more distant exoplanets where we have far less data to work with. There's also the disk sculpting question we discussed earlier. With a confirmed planet now located right at the disk's inner edge, expect a wave of new modeling papers attempting to explain the disk's various warps, gaps, and asymmetries, using Beta Pictoris D's confirmed properties as an input, testing whether this newly found planet can account for structural features that puzzled astronomers for decades. And then there's the broader search implication we spent so much time on earlier. Expect other research teams to start applying similar spectroscopic search techniques to other dusty, disk-rich systems that have previously resisted conventional direct imaging searches. Systems like Fomalhaut, O-microscopy, and various other young, disk-bearing stars are natural next candidates for this kind of chemistry-first search strategy. If even a modest fraction of those systems turn out to be hiding giant planets the same way Beta Pictoris was, the known population of directly detected exoplanets could grow meaningfully over the next several years, driven specifically by this new detection channel. It's also worth noting the sheer symbolic weight of this discovery landing on this particular star. Beta Pictoris has been a flagship system in exoplanet science since 1984, the very first directly imaged debris disk, one of the very first directly imaged exoplanets in Beta Pictoris b, and now, over 4 decades later, a demonstration of an entirely new detection method with the discovery of Beta Pictoris d. It's almost poetic that a system responsible for so many firsts in this field just delivered another one. For a star system that's been under nearly continuous scientific scrutiny since before some of the astronomers currently studying it were even born, the fact that it still had a secret left to reveal is a humbling reminder about how much remains to be discovered, even in the places we think we know best. Here's what I find most compelling about this whole story, more than the specific numbers about mass and orbital distance and molecular abundances, as fascinating as those details are. Beta Pictoris d was there the entire time. Every photograph taken of that system since 1984 technically contained the light, or at least the gravitational fingerprint, of this planet. It wasn't newly formed. It wasn't a fluke of timing. It was simply hiding, using nothing more exotic than ordinary scattered starlight and dust, in front of some of the most sophisticated instruments humanity has ever built to look for exactly this kind of object. What changed wasn't the planet. What changed was the question astronomers knew how to ask. For decades, the question was, where is the bright dot? The answer, finally, came from asking an entirely different question. What does this system's chemistry tell us that its brightness alone never could? That shift from looking for light to reading chemistry might end up being the more lasting legacy of this discovery than the planet itself. Every dusty, complicated, previously fully explored system out there just became, once again, a place worth looking harder. If you enjoyed this deep dive into one of the most elegant exoplanet discoveries of the decade, let me know in the comments which system you'd want to see this technique applied to next. And if you want to understand how James Webb keeps rewriting what we thought we already knew about the universe, there are more stories just like this one waiting in this channel. Because if a planet can hide in plain sight for 40 years around one of the most photographed stars in the sky, it makes you wonder what else is still out there, quietly waiting to be found. It's also worth noting the sheer symbolic weight of this discovery landing on this particular star. Beta Pictoris has been a flagship system in exoplanet science since 1984, the very first directly imaged debris disk, one of the very first directly imaged exoplanets in Beta Pictoris b, and now, over 4 decades later, a demonstration of an entirely new detection method with the discovery of Beta Pictoris d.